Imagine you're sitting in a chair right now. You feel solid. The chair feels solid. The ground beneath you feels completely still and stable. Everything around you seems fixed in place, unchanging, permanent. But what if I told you that's an illusion? What if the space around you isn't empty at all, but is actually a fabric that can bend, twist, stretch, and even tear? What if time itself isn't constant, but flows at different speeds depending on where you are and how fast you're moving? What if everything you think you know about reality is wrong? In 1905, a 26-year-old patent clerk in Switzerland, working in his spare time, discovered something that changed everything. His name was Albert Einstein. And what he found was so strange, so impossible sounding, that even he struggled to believe it at first. He discovered that space and time aren't separate things. They're woven together into a single fabric called spacetime. And this fabric isn't just a background where things happen. It's an active player in the universe. It bends around massive objects like stars and planets. It ripples when violent cosmic events occur. It can even create tunnels connecting distant parts of the universe. Einstein's discovery revealed that the universe is far stranger than anyone had imagined. Time can slow down. Space can curve. Gravity isn't a force pulling things together. It's the shape of space-time itself. And here's the truly mind-bending part. We've proven all of this is real. We've measured time running slower on airplanes. We've detected ripples in space-time from black holes colliding billions of light years away. We've used Einstein's equations to build the GPS satellites that help you navigate every day. But even now, more than a century later, we still don't fully understand space-time. There are mysteries hidden in Einstein's equations, paradoxes that seem impossible, questions that challenge everything we think we know about reality. What happens to space-time inside a black hole? Can we use it to travel through time? Does space-time break down at the smallest scales? And the biggest question of all, what is space-time really made of? Stay with me, because what you're about to discover will change how you see the universe forever. Welcome back to Science for Sleep. If you're new here, you've just entered a journey into one of the deepest mysteries in all of science. And if you're returning, thank you for joining me once again as we explore the nature of reality itself. Today, we're going to spend the next 2.5 hours unraveling one of the most profound discoveries in human history. Einstein's revelation that space and time are not what they seem, that they're not separate, independent things, but are instead woven together into a dynamic, flexible fabric that shapes everything in the universe. This isn't a quick summary. This is a complete journey through the science, the history, the mind-bending implications, and the mysteries that still puzzle scientists today. We're going to understand not just what space-time is, but why it matters, how it was discovered, and what it means for the future of physics and our understanding of the cosmos. We'll start with the world before Einstein, when people believed space was just empty nothingness and time ticked away, the same for everyone, everywhere. We'll follow the clues that didn't quite add up, the experiments that gave impossible results, and the moment Einstein put all the pieces together. We'll explore special relativity, Where Einstein showed that time can slow down and space can shrink when you move fast enough. We'll dive into general relativity, where he revealed that gravity isn't a force at all, but is the bending of space-time itself by massive objects. We'll see the evidence that proved Einstein right, from the bending of starlight around the sun to the detection of gravitational waves from colliding black holes. We'll understand how GPS satellites use Einstein's equations every single day, and how time literally runs slower on Earth's surface than it does in orbit. We'll confront the paradoxes and puzzles. A twin paradox, where one twin ages faster than the other. The possibility of time travel. The singularities inside black holes, where space-time seems to break down completely. The conflict between general relativity and quantum mechanics that has haunted physics for nearly a century. And we'll explore the cutting edge of research. Scientists searching for quantum gravity. Physicists wondering if space-time is fundamental or emerges from something deeper. Experiments looking for the smallest possible unit of space and time. This is the kind of deep exploration you can settle in with, whether you're actively learning or letting your mind wander through the cosmos while you relax or drift off. Every chapter builds understanding, revealing the elegant structure of Einstein's universe, piece by piece. So get comfortable, take a breath, and prepare to see reality in a completely new way. Because the truth about space-time is stranger, more beautiful, and more mind-bending than you ever imagined. Let's begin at the beginning. In a world that believed space and time were absolute and unchanging. A world that was about to be turned upside down. To understand how revolutionary Einstein's ideas were, we need to go back to the world before him. A world where space and time seemed simple, obvious, and absolute. For thousands of years, humans looked up at the sky and saw the same basic picture. The Earth sat at the center of everything. The sun, moon, planets, and stars all revolved around us. Space was just the empty void where these objects moved. Time was the steady rhythm that measured their movements. Then came the scientific revolution. Nicolaus Copernicus showed that Earth wasn't the center. We orbit the sun along with the other planets. Galileo Galilei used a telescope to see moons orbiting Jupiter and craters on our own moon, proving that celestial objects weren't perfect and unchanging. But the biggest breakthrough came from Isaac Newton in the late 1600s. Newton discovered the laws of motion and the law of universal gravitation. And in doing so, he created a framework for understanding space and time that would dominate physics for more than 200 years. Newton's vision was elegant and powerful. Space, he said, was like an infinite, invisible grid stretching in all directions. It was absolute and unchanging. A meter was a meter everywhere in the universe. Whether you were on Earth or on Mars, or floating in the void between galaxies, distances were the same. Time, Newton said, was also absolute. It flowed at the same rate everywhere, for everyone, no matter what. If a second passed for you, a second passed for every person, every object, everywhere in the universe simultaneously. Time was like a cosmic clock that ticked the same for all of reality. This made intuitive sense. It matched everyday experience. If you and a friend both have accurate clocks, and you synchronize them, they should stay synchronized whether you're standing next to each other or on opposite sides of the planet. Time is time. It doesn't change. In Newton's universe, space provided the stage where events happened, and time was the universal clock that measured when they happened. They were completely separate. Space was space. Time was time. They didn't interact or influence each other in any way. Newton's laws of motion described how objects move through this space over time. An object at rest stays at rest unless a force acts on it. An object in motion stays in motion at constant speed in a straight line unless a force changes that. For every action, there's an equal and opposite reaction. These laws worked beautifully. They explained how planets orbit the sun, how cannonballs arc through the air, how pendulums swing. Engineers used them to build machines. Astronomers used them to predict the positions of planets and comets decades in advance. Newton also discovered the law of universal gravitation. Every object with mass, he said, attracts every other object with mass. The force depends on how much mass the objects have and how far apart they are. More massive objects create stronger gravitational pull. Objects farther apart feel weaker gravitational attraction. This explained why planets orbit the sun. The sun's enormous mass pulls on them. It explained why we don't float off into space. Earth's mass pulls us down. It explained ocean tides caused by the moon's gravitational pull on Earth's water. For over 2 centuries, Newton's framework reigned supreme. It was tested over and over and kept working. Scientists discovered new planets using Newton's laws. They predicted solar eclipses. They calculated the paths of comets. Everything fit together perfectly. But by the late 1800s, tiny cracks began to appear. Strange results from experiments that didn't quite make sense in Newton's framework. Observations that hinted something wasn't quite right. One of the biggest puzzles involved light. Scientists had figured out that light is a wave similar to water waves or sound waves, but made of oscillating electric and magnetic fields. These waves are called electromagnetic waves. But here's the thing about waves. They need something to wave through. Water waves travel through water. Sound waves travel through air or other materials. What did light waves travel through? Since light can travel through empty space, we see light from the sun and stars. After all, scientists concluded there must be some invisible substance filling all of space. They called it the ether or the luminiferous ether. Light waves, they believed, were ripples in this ether. The ether was supposed to be everywhere, filling space between the stars, permeating everything. It had to be incredibly thin and light, since we couldn't detect it directly, and it didn't seem to slow down the motion of planets. But it had to be there. Otherwise, how could light waves travel? In 1887, 2 American scientists, Albert Michelson and Edward Morley, set up an experiment to detect the ether. Their reasoning was clever. Earth moves through space as it orbits the sun at about 30 kilometers per second. If space is filled with ether, then Earth must be moving through this ether, like a boat moving through water. When a boat moves through water, the water flows past the boat. If you measure the speed of waves in the water, you get different results depending on whether the waves are moving with the boat, against the boat, or perpendicular to the boat's motion. Michelson and Morley figured the same should be true for light moving through the ether. As Earth moves through space, we should be moving through the ether. Light traveling in the direction of Earth's motion should have a different speed than light traveling perpendicular to Earth's motion. They built an extremely sensitive instrument called an interferometer to measure this difference. They split a beam of light, sent the two parts in perpendicular directions, bounced them off mirrors, and brought them back together. If light traveled at different speeds in different directions through the ether, the two beams would be slightly out of sync when they recombined, creating an interference pattern. They ran the experiment, and the result was shocking. There was no difference. Light traveled at exactly the same speed in all directions, regardless of Earth's motion through space. It was as if the ether didn't exist at all. Or if it did exist, Earth wasn't moving through it, which made no sense because we knew Earth orbits the Sun. Scientists tried to explain this strange result. Maybe Earth drags the ether along with it as it moves? But that didn't work because other observations contradicted it. Maybe the ether behaves in some weird way we don't understand, but every explanation seemed contrived and unsatisfying. The Michelson-Morley experiment was a huge puzzle, and it was just one of several problems building up in physics. Another involved the orbit of Mercury. Mercury is the planet closest to the Sun. Astronomers had been tracking its orbit very precisely for decades. Newton's laws predicted almost perfectly where Mercury would be at any given time. Almost, but not quite. Mercury's orbit isn't a perfect circle. It's an ellipse, an oval shape. And this ellipse itself rotates very slowly over time. The point where Mercury comes closest to the Sun gradually shifts, a phenomenon called the precession of perihelion. Most of this precession could be explained by the gravitational pull of other planets. But there was a tiny discrepancy. Mercury's orbit precessed slightly more than Newton's laws predicted. The difference was tiny only, about 43 arcseconds per century. An arcsecond is 1 by 3,600th of a degree, so 43 arcseconds is an incredibly small angle. But it was real, and it couldn't be explained. Some astronomers proposed there might be an unknown planet even closer to the Sun than Mercury, whose gravity caused the extra precession. They even gave it a name, Vulcan. But despite extensive searches, no such planet was ever found. There were other puzzles too. The behavior of objects moving at very high speeds didn't quite match predictions. Certain properties of atoms and molecules seemed strange. Light from distant stars appeared to bend slightly when passing near the Sun, visible during solar eclipses. But the amount of bending wasn't quite what Newton's theory predicted. By the turn of the 20th century, physics was in a strange state. On one hand, it was incredibly successful. Newton's laws worked for almost everything. Engineers built bridges and machines. Astronomers predicted planetary positions. The framework seemed solid. But these tiny anomalies kept nagging at scientists. The constant speed of light regardless of motion through the ether. Mercury's odd orbit. strange behaviors at high speeds. It felt like there were small pieces that didn't quite fit. Most physicists assumed these were minor problems that would eventually be resolved within Newton's framework. Maybe the ether behaved in some complicated way that hadn't been discovered yet. Maybe there were small corrections to Newton's laws that would fix the discrepancies. Nobody expected that the entire foundation of physics was about to be torn down and rebuilt. Nobody expected that space and time themselves were about to be revolutionized. But in 1905, a young man working at a patent office in Bern, Switzerland, was thinking deeply about these problems. He wasn't famous. He didn't have a position at a prestigious university. He was just a curious mind, fascinated by the puzzles of nature. His name was Albert Einstein, and he was about to change everything. Albert Einstein was born on March 14, 1879, in the city of Ulm, in what is now Germany. From a young age, he was curious about how the world worked, but he wasn't a child prodigy or a perfect student. In fact, there's a myth that Einstein did poorly in school, but that's not quite true. Einstein did well in subjects he was interested in, especially mathematics and physics. But he struggled with the rigid, authoritarian style of education in Germany at the time. He questioned teachers, challenged assumptions, and often found the rote memorization approach boring and pointless. When Einstein was 15, his family moved to Italy for business reasons, but he stayed behind in Germany to finish school. He was unhappy, felt stifled by the educational system, and eventually left school without graduating. He later took the entrance exam for the Swiss Federal Polytechnic in Zurich, but failed the general part, though he excelled in mathematics and physics. After some additional preparation, Einstein was admitted to the Polytechnic in 1896. There, he studied physics and mathematics, but he often skipped classes to read the works of great physicists on his own. He was more interested in understanding the deep principles of nature than in memorizing facts for exams. His professors weren't always impressed. One professor, Hermann Minkowski, described Einstein as a lazy dog who rarely attended lectures. But Einstein's friend Marcel Grossmann took excellent notes that Einstein borrowed to prepare for exams. Despite his unconventional approach, Einstein passed his exams and graduated in 1900. But then he faced a problem. He couldn't find an academic position. His habit of skipping classes and questioning authority hadn't endeared him to his professors, and they didn't offer him the recommendations he needed. For 2 years, Einstein struggled to find work. He took temporary teaching jobs, tutoring students in mathematics and physics. It was a difficult time, filled with uncertainty and financial hardship. Finally, in 1902, with the help of his friend Marcel Grossmann's father, Einstein got a job at the Swiss Patent Office in Bern. His position was technical expert third class, which meant he reviewed patent applications for new inventions, checking whether they were practical and whether the claims made sense. This might seem like a step down for someone with Einstein's talent, but in some ways, it was perfect for him. The job wasn't too demanding, leaving him time to think about physics. And reviewing patents trained him to visualize how machines and devices worked, which sharpened his ability to do thought experiments, imagining physical. situations, and reasoning through what would happen. Einstein would finish his patent work quickly, then spend the rest of his time thinking about the deep questions in physics. He had no access to advanced laboratory equipment, no graduate students to help him, no colleagues to discuss ideas with. Just his mind, some paper, and a passion for understanding the universe. In his spare time, Einstein thought obsessively about the puzzle of light and the ether. The Michelson-Morley experiment had shown that light always travels at the same speed, regardless of how the observer is moving. But how could that be? In Newton's universe, speeds add together. If you're on a train moving at 50 kilometers per hour, and you throw a ball forward at 20 kilometers per hour, someone standing on the ground sees the ball moving at 70 kilometers per hour, the train's speed plus the ball's speed. Similarly, if you're moving toward a source of light, you should measure the light coming toward you faster. If you're moving away from the light source, you should measure it slower. But the Michelson-Morley experiment showed this didn't happen. Light always traveled at the same speed, no matter what. Einstein realized that most physicists were trying to explain this by making the ether more complicated. But he started to consider a radical alternative. What if there is no ether? What if light just travels at a constant speed through empty space? And this speed is the same for all observers, no matter how they're moving? This idea seemed crazy. It violated common sense. It contradicted Newton's principles. But Einstein started to take it seriously. He also thought about something else. The laws of physics should be the same for everyone, no matter how they're moving, as long as they're moving at constant speed in a straight line. This principle was called the principle of relativity, and it went back to Galileo. Imagine you're sitting in a train moving smoothly at constant speed. If you drop a ball, it falls straight down from your perspective. If you toss a ball to a friend across the aisle, it moves in a straight line from your perspective. You can't tell you're moving just by doing experiments inside the train. This makes sense. Motion at constant speed should be relative. There's no absolute reference frame. From your perspective on the train, you're at rest and the landscape outside is moving. From someone on the ground's perspective, the train is moving and they're at rest. Neither perspective is more correct than the other. But there was a problem. Newton's laws of motion obeyed this principle of relativity. But the laws of electromagnetism, the laws describing how light and electromagnetic waves behave, didn't seem to. They seemed to depend on the ether, which would provide an absolute reference frame. Einstein wrestled with this contradiction. He wanted to preserve the principle of relativity, that the laws of physics are the same for all observers moving at constant speed. But he also wanted to accept the experimental result, that light travels at a constant speed for all observers. In May 1905, after years of thought, something clicked. Einstein realized that these two principles, the principle of relativity and the constancy of the speed of light, could both be true. But accepting them both required giving up something fundamental, the idea that space and time are absolute. Einstein understood that if light always travels at the same speed for everyone, then space and time must be flexible. They must adjust themselves to keep the speed of light constant. An observer moving relative to you doesn't just see things in different places. They actually experience space and time differently than you do. Time can pass at different rates for different observers. Distances can shrink or stretch depending on how fast you're moving. The concepts of now and simultaneous aren't absolute. Events that happen at the same time for one observer might happen at different times for another observer. This was stunning. It meant that the entire Newtonian framework, which had worked so well for 2 centuries, was only an approximation. It worked fine at everyday speeds, but at speeds approaching the speed of light, space and time behave in completely unexpected ways. Einstein wrote up his ideas in a paper titled On the Electrodynamics of Moving Bodies. He submitted it to a prestigious physics journal called Annalen der Physik in June 1905. The paper was published in September. This was the birth of special relativity, and it would change physics forever. But 1905 wasn't done. Einstein didn't just write one revolutionary paper that year. He wrote 4 papers, each one groundbreaking, each one worthy of a Nobel Prize. In March, he published a paper on the photoelectric effect, showing that light behaves as if it's made of tiny particles called photons. This helped establish quantum theory and eventually earned Einstein the Nobel Prize in 1921. In April, he completed his doctoral dissertation, which calculated the size of molecules by studying their effects on liquids. It was a tour de force of statistical physics. In July, he published a paper on Brownian motion, the random jiggling of tiny particles suspended in a fluid. Einstein showed this motion was caused by molecules of the fluid constantly bumping into the particles. This provided strong evidence that atoms and molecules are real, something that wasn't universally accepted at the time. And in September, after his relativity paper, he published a short follow-up that contained perhaps the most famous equation in all of physics: E equals mc squared. Energy equals mass times the speed of light squared. This equation revealed that mass and energy are equivalent. They're different forms of the same thing. A small amount of mass contains an enormous amount of energy because the speed of light is such a large number, and you square it. This equation would eventually lead to nuclear power and nuclear weapons. It explained how the sun shines by converting a tiny fraction of its mass into energy through nuclear fusion. It showed that mass itself is a concentrated form of energy. All of this came from a 26-year-old patent clerk working in his spare time, with no laboratory, no research team, no funding. Just pure thought, imagination, and a deep commitment to understanding how nature works. The physics community was slow to notice. Einstein's papers were published, but they didn't immediately cause a sensation. Relativity was strange and counterintuitive. Many physicists initially ignored it or didn't understand it, but gradually word spread. A few physicists recognized the significance of what Einstein had done. They started teaching his ideas, testing his predictions, and building on his work. By 1909, Einstein's fame was growing. He left the patent office and took academic positions, first at the University of Zurich and in Prague, then back in Zurich at his alma mater, the Polytechnic. But Einstein wasn't done. Special relativity was incredible, but it had a limitation. It only applied to observers moving at constant speed. It didn't include acceleration or gravity. Einstein wanted to extend relativity to include all types of motion, including accelerated motion and gravitational fields. This would require an even more radical rethinking of space and time. He spent the next 10 years, from 1905 to 1915, working on this problem. It was incredibly difficult. The mathematics was far more complex than for special relativity. Einstein struggled, made mistakes, went down wrong paths, and sometimes felt like giving up. But he kept going. And in 1915, he finally completed his masterpiece, the general theory of relativity, a theory that would reveal that gravity isn't a force at all, but is the curvature of space-time itself. This theory would predict black holes, the expansion of the universe, gravitational waves, and the bending of light by massive objects. It would pass every experimental test thrown at it for more than a century. And it would establish Einstein as perhaps the greatest physicist since Newton, a thinker who fundamentally changed how we understand reality. But before we get to general relativity, we need to understand special relativity, because you can't appreciate the full strangeness of space-time until you see how. Einstein first revealed that space and time are not what they seem. Let's start with the simplest, most shocking prediction of special relativity. Time is not absolute. Time can pass at different rates for different people. This is called time dilation, and it's one of the strangest consequences of Einstein's theory. To understand it, we need to start with Einstein's two basic principles. Principle 1. The laws of physics are the same for all observers moving at constant speed in a straight line. There's no experiment you can do to determine absolute motion. You can only measure your motion relative to something else. Principle 2. The speed of light in empty space is always the same for all observers, regardless of how they're moving. It doesn't matter if you're moving toward the light source or away from it. Light always travels at 299,792,458 meters per second, usually rounded to 300,000 kilometers per second. These two principles might seem innocent, but accepting them both leads to mind-bending consequences. Let me show you with a thought experiment. Imagine a spaceship traveling through space at half the speed of light. That's 150,000 kilometers per second. Incredibly fast by human standards, but only half of light speed. Inside the spaceship, there's a simple device. A light source on the floor sends a beam of light up to a mirror on the ceiling, 3 meters away. The light bounces off the mirror and comes back down to a detector next to the light source. From the perspective of someone on the spaceship, this is simple. The light travels 3 meters up to the mirror, then 3 meters back down, for a total distance of 6 meters. Since light travels at 300,000 kilometers per second, the time for this round trip is incredibly short, but we can calculate it. 6 meters divided by 300 million meters per second equals 20 nanoseconds. That's how long the light takes to make the round trip from the astronaut's perspective. Now let's look at this from the perspective of someone watching the spaceship fly by. We'll call them the Earth observer. From the Earth observer's perspective, the spaceship is moving. While the light travels from the floor to the ceiling, the spaceship moves forward. So the light doesn't travel straight up, it travels diagonally, going up and forward at the same time. Similarly, on the return trip, the light travels down and forward. The light's path from the Earth observer's perspective is a diagonal up, then a diagonal down, forming a triangular path. This diagonal path is longer than the straight up and down path the astronaut sees. Basic geometry tells us the diagonal of a triangle is longer than just the height of the triangle. But here's the critical point. The speed of light must be the same for both observers. That's the second principle of relativity. The Earth observer measures light traveling at exactly 300,000 kilometers per second, the same speed the astronaut measures. If the light has to travel a longer path, but at the same speed, it must take more time. The Earth observer sees the light take longer to complete its round trip than the astronaut does. Let's think about what this means. For the astronaut, 20 nanoseconds pass during the light's round trip. For the Earth observer, more time passes, let's say 23 nanoseconds for a spaceship moving at half light speed. But the astronaut's heartbeat, their breathing, their thoughts, all of these are physical processes happening at the same time as the light bouncing up and down. If the light's round trip takes longer from the Earth observer's perspective, then all these other processes must also take longer from the Earth observer's perspective. From the Earth observer's viewpoint, time itself is passing more slowly for the astronaut. The astronaut's clock is ticking slower. Their heart is beating slower. They're aging slower. This isn't an illusion or a trick. Time is genuinely passing at different rates. This is time dilation. The effect gets more extreme as you go faster. At 90% the speed of light, time dilation is dramatic. If the astronaut experiences 1 year passing, the Earth observer sees more than 2 years pass. At 99% the speed of light, 1 year for the astronaut is about 7 years for the Earth observer. As you approach the speed of light, time dilation becomes more and more extreme. At 99.9% the speed of light, 1 year for the astronaut is more than 20 years for the Earth observer. And here's the crucial point. This effect is completely symmetric. From the Earth observer's perspective, the astronaut's time is slowed down. But from the astronaut's perspective, they're at rest, and the Earth observer is moving away at high speed. So the astronaut sees the Earth observer's time as slowed down. This might seem like a contradiction. How can each person think the other's time is slower? But it's not a contradiction because of something called the relativity of simultaneity, which we'll explore more later. The key is that when observers are moving relative to each other, they don't agree on which events happen at the same time. Now, you might be thinking, this is just a theoretical prediction. Does time dilation actually happen in reality? Yes, it absolutely does, and we've measured it many times. One of the first confirmations came from studying particles called muons. Muons are created when cosmic rays from space hit the upper atmosphere. They're unstable particles that decay into other particles very quickly. A muon only lives for about 2.2 microseconds on average before it decays. Muons are created about 15 kilometers up in the atmosphere. Traveling even at close to the speed of light, they should only make it about 660 meters before decaying. They shouldn't reach the ground, but they do. We detect muons at ground level all the time. In fact, about 1 won passes through your hand every second. How do they make it? Time dilation. The muons are traveling at about 99.8% the speed of light. At that speed, time dilation is significant. From our perspective on the ground, the muons' internal clocks are running slow. They decay much more slowly than they would if they were at rest. This gives them time to reach the ground before decaying. From the muon's perspective, it's a bit different. The muon experiences 2.2 microseconds before decaying. But from the muon's viewpoint, space itself is contracted. The 15 kilometers of atmosphere is squished down to about 300 meters. So the muon has plenty of time to travel through the thin atmosphere before it decays. Both perspectives are correct. Time dilation and space contraction are two sides of the same coin. We've also tested time dilation directly with atomic clocks. In 1971, scientists Joseph Haffel and Richard Keating took 4 atomic clocks on commercial airplane flights around the world. Some clocks flew eastward, others westward. When they compared these clocks to identical clocks that stayed on the ground, they found tiny differences. The flying clocks showed slightly less time had passed than the ground clocks. The difference was only a few hundred nanoseconds, but it matched Einstein's predictions precisely. The effect happens because the airplane clocks were moving faster relative to the Earth's center than the ground clocks were. This caused time dilation. There was also an effect from being higher up in Earth's gravitational field, which we'll talk about when we get to general relativity. Today, we have to account for time dilation constantly in GPS satellites. These satellites orbit Earth at about 14,000 kilometers per hour, and they're about 20,000 kilometers above the surface. Because they're moving fast, time dilation causes their clocks to run slow compared to clocks on Earth. But because they're higher up in Earth's gravitational field, their clocks run fast compared to Earth clocks. Both effects matter. If we didn't correct for these effects, GPS would accumulate errors of about 10 kilometers per day. Your phone's GPS would be useless. The fact that GPS works so well is daily proof that Einstein was right about time dilation. But time dilation creates a famous paradox. It's called the twin paradox, and it seems to lead to a contradiction. Imagine 2 twins, Alice and Bob. Alice gets on a spaceship and travels to a nearby star at 99% the speed of light. The journey takes a few years from her perspective. Then she turns around and comes back to Earth at the same speed. From Alice's perspective, Bob is moving away and then coming back. So Alice thinks Bob's time should be running slow, and Bob should be younger when they reunite. But from Bob's perspective, Alice is the one moving away and coming back. So Bob thinks Alice's time should be running slow, and Alice should be younger when they reunite. They can't both be right. When Alice returns to Earth, one of them must be older than the other. So who is it? The answer is that Alice will be younger. Bob will have aged more. And this isn't a contradiction, because the situation isn't actually symmetric. Bob stayed in one inertial reference frame the whole time he was moving at constant velocity. But Alice didn't. She had to accelerate when leaving Earth, decelerate when arriving at the star, accelerate to turn around, and decelerate when returning to Earth. Alice's experience involved acceleration, which makes her situation different from Bob's. The proper way to analyze this is with general relativity, which includes acceleration and gravity. But the bottom line is clear. Alice experiences less time than Bob. If Alice travels for 1 year on her spaceship clock, perhaps 10 years pass on Earth. She returns younger than her twin. This isn't science fiction. It's real physics. If we ever develop spacecraft that can travel at a significant fraction of light speed, astronauts will experience this effect. They could travel to distant stars and return to find that centuries have passed on Earth, while only years passed for them. Time dilation tells us something profound. Time is not a universal, absolute thing that ticks the same for everyone. Time is personal. Your experience of time depends on how you're moving through space. Space and time are not separate, independent things. They're intimately connected. What one person experiences as space, another person experiences as a mixture of space and time. They're part of a unified whole. This unified whole is what we call spacetime. And understanding spacetime is the key to understanding Einstein's revolution. If time can dilate, what happens to space? Einstein's answer is equally strange. Space shrinks when you're moving at high speeds. This is called length contraction. Let's go back to our spaceship, traveling at half the speed of light. From the perspective of someone on the ground, watching the spaceship fly by, the ship looks shorter than it does to the astronauts inside. This isn't an optical illusion. The spaceship is actually shorter in the direction it's moving. If the spaceship is 100 meters long when at rest, when it's moving at half the speed of light, it measures only about 87 meters long from the Earth observer's perspective. The astronauts inside don't notice anything strange. From their perspective, they're at rest, and the spaceship is its normal 100-meter length. But they see space outside contracted. Distances between stars appear shorter than they would if the spaceship were at rest. Again, this effect is symmetric. The Earth observer sees the spaceship contracted. The astronauts see Earth, and all its structures contracted in the direction of motion. Length contraction gets more extreme as speed increases. At 90% the speed of light, length contracts to about 44% of its rest length. At 99% light speed, it's about 14%. At 99.9% light speed, it's less than 5%. Let's think about what this means. Imagine you're an astronaut traveling to a star 10 light years away at 99.9% the speed of light. From Earth's perspective, you're traveling 10 light years at almost light speed, so it takes a little over 10 years. But from your perspective, something amazing happens. The distance to the star is contracted. It's not 10 light years, it's less than half a light year. You experience only about 6 months of travel time because, from your reference frame, the distance is much shorter. This matches up with time dilation. From Earth's perspective, your clock runs slow. So even though 10 years pass on Earth, you experience less time. From your perspective, you experience normal time, but the distance is shorter. Both perspectives agree on what actually happens. You make the journey, but they describe it differently. The connection between time dilation and length contraction reveals something deep. Space and time are not independent. They're different aspects of a single four-dimensional entity called spacetime. Think about it this way. Imagine you're looking at a long stick lying on the ground. If you look at it from one angle, you see its full length. If you look at it from a different angle, you see it foreshortened. It looks shorter because you're viewing it at an angle. In a similar way, observers moving relative to each other are viewing spacetime from different angles. What one observer sees as pure space, another observer sees as a mixture of space and time. What one measures as length, another measures as a combination of length and duration. In spacetime, there's no absolute division between space and time. The division depends on your perspective, on how you're moving. Space-time is the fundamental thing. Space and time are just different ways of slicing up space-time, depending on your reference frame. This was a revolutionary insight. Before Einstein, we thought of the universe as three-dimensional space that changes over time. Einstein showed us we live in a four-dimensional space-time. 3 dimensions of space, 1 dimension of time, all woven together into a single fabric. Now, length contraction leads to some strange situations. Here's a famous thought experiment called the ladder paradox. Imagine you have a ladder that's 10 meters long. There's a garage with doors on both ends that's also 10 meters long. When the ladder is at rest in the garage, it just barely fits. The back door closes just as the front of the ladder reaches it. Now, someone runs very fast, carrying the ladder toward the garage. Let's say they run at 90% the speed of light. From the perspective of someone standing by the garage, the moving ladder is length contracted. It's only about 4.4 meters long. So the ladder easily fits inside the garage with room to spare. Both garage doors can be closed simultaneously with the ladder completely inside. But from the perspective of the person carrying the ladder, they're at rest, and the ladder is 10 meters long. The garage is moving toward them at 90% light speed, so the garage is length contracted. It's only about 4.4 meters long. There's no way the 10-meter ladder can fit inside the 4.4-meter garage. So does the ladder fit inside the garage or not? Both perspectives seem equally valid, but they give opposite answers. This seems like a paradox. The resolution is the relativity of simultaneity. The key word in the garage observer's description was simultaneously. They said both garage doors can be closed simultaneously with the ladder inside. But simultaneity is relative. Events that are simultaneous for one observer are not simultaneous for another observer in a different reference frame. From the garage observer's perspective, both doors close at the same time, briefly trapping the contracted ladder inside. Then the doors open before the ladder crashes into them. From the ladder carrier's perspective, the doors don't close at the same time. The front door closes first. The ladder starts to enter the garage. Then the front door opens. Later, after the ladder is mostly through the garage, the back door closes and opens. The latter is never completely inside the closed garage. Both descriptions are correct. They're just different ways of describing the same sequence of events in space-time. The events themselves, the closing and opening of each door, the latter entering and exiting, are real and agreed upon. But the timing relationships between these events differ depending on your reference frame. This is what Einstein meant when he said that simultaneity is relative. There's no absolute now that extends across all of space. Different observers in relative motion have different nows. They slice up space-time in different ways. This has profound implications. In Newton's universe, we could imagine freezing time for the entire universe at once, taking a snapshot of everything everywhere at a single instant. But in Einstein's universe, there's no such universal instant. There's no objective way to say that a distant event is happening now versus in the past or future. Your now extends across all of space from your perspective. But someone moving relative to you has a different now that includes some events you consider in your future and excludes some events you consider in your present. This sounds crazy, but it's a direct consequence of the constancy of the speed of light combined with the principle of relativity. Let's think about what all this means for our understanding of reality. Special relativity tells us time is not absolute. It passes at different rates for different observers, depending on their relative motion. Space is not absolute. Distances and lengths depend on the observer's motion. Simultaneity is not absolute. Events that happen at the same time for one observer happen at different times for another. The speed of light is absolute. It's the one thing that's the same for all observers, regardless of their motion. And there's one more crucial insight. Nothing can travel faster than light. The speed of light is the ultimate speed limit of the universe. Why? The mathematics of special relativity makes this clear. As an object with mass approaches the speed of light, its energy increases without bound. It would take infinite energy to accelerate something with mass all the way to light speed. So light speed is impossible to reach for anything with mass. Light itself travels at light speed because photons, the particles of light, have no mass. Anything with zero mass must travel at light speed. Anything with mass must travel slower than light speed. This speed limit isn't just a practical limitation of our technology. It's a fundamental feature of how space-time works, and it has enormous implications. For one thing, it means there's no such thing as instantaneous action at a distance. You can't send a signal or exert an influence faster than light. If the sun suddenly disappeared, Earth wouldn't immediately fly off into space. We'd keep orbiting for about 8 minutes, the time it takes for light to travel from the sun to Earth before we felt any effect. The speed of light limit also means that cause and effect are preserved. If one event causes another event, the cause must happen before the effect for all observers. The speed of light limit ensures this consistency. If faster than light travel were possible, it would allow for time paradoxes. You could potentially send signals into your own past, creating situations where an effect happens before its cause. But the speed of light limit prevents these paradoxes. Special relativity shows us that space and time are flexible, relative, and intertwined. But they're not arbitrary. There are rules. The speed of light is the cosmic speed limit. Spacetime has a structure that's consistent and predictable, even though it's stranger than we ever imagined. This was Einstein's achievement in 1905. He revealed that the universe doesn't work the way Newton thought. Space and time are not the rigid stage where physics happens. They're dynamic, flexible, and intimately connected to each other and to the matter and energy in the universe. But special relativity only applied to constant speed motion. It didn't include acceleration or gravity. Einstein knew this was a limitation, and for the next 10 years, he struggled to extend relativity to include all types of motion and to understand what gravity really is. The answer he found was even more mind-blowing than special relativity. It required a complete reimagining of gravity itself, and it revealed that space-time isn't just flexible. It can curve, twist, and stretch in ways that create some of the most extreme and bizarre phenomena in the universe. By 1907, special relativity was gaining acceptance in the physics community. But Einstein knew it was incomplete. It worked for objects moving at constant speed, but it didn't include acceleration. And it didn't explain gravity. Gravity was a huge problem. Newton's law of gravity said that two masses attract each other with a force that depends on their masses and the distance between them. The force acts instantaneously. If the sun suddenly moved, Earth would immediately feel a change in gravitational force. But special relativity said nothing can travel faster than light, including gravitational effects. So Newton's instantaneous gravity violated special relativity. Something was wrong. Einstein thought about this puzzle constantly. How could he extend relativity to include gravity? What was gravity really? Then, in 1907, Einstein had what he later called the happiest thought of my life. He was sitting in his chair at the patent office in Bern when a simple idea struck him. If a person is falling freely, they don't feel their own weight. They feel weightless. Think about it. When you're standing on the ground, you feel the force of gravity pulling you down. But you also feel the ground pushing up on your feet. These two forces balance, keeping you stationary. What you experience as the feeling of weight is actually the ground pushing up on you. Now imagine you're in an elevator and the cable breaks. You and the elevator both start falling. During those terrible seconds of free fall, you would feel weightless. You wouldn't feel any force. The floor of the elevator wouldn't be pushing up on your feet because it's falling at the same rate you are. From your perspective inside the falling elevator, it would be as if gravity had been turned off. You could float around the elevator. If you let go of an object, it would just hover in place relative to you because it's also falling at the same rate. This is actually how astronauts on the International Space Station experience weightlessness. The station is constantly falling toward Earth, but it's also moving sideways fast enough that it keeps missing Earth. This continuous free fall creates the sensation of weightlessness. Einstein realized this simple observation was profound. In free fall, gravity disappears. Or more precisely, you can't tell the difference between being in free fall in a gravitational field and floating in empty space far from any gravitational sources. This led Einstein to his equivalence principle. Being in free fall in a gravitational field is equivalent to being in an inertial reference frame, moving at constant velocity, far from any gravity. You can't do any local experiment to tell the difference between these two situations. Think about astronauts in orbit. They're in free fall around Earth. From their perspective, they're weightless and floating. They could do experiments, and those experiments would give the same results as if they were floating in deep space, far from any stars or planets. But Einstein realized the equivalence principle also works the other way. Being at rest in a gravitational field is equivalent to being in an accelerating reference frame. Imagine you're in a rocket ship in deep space, far from any gravity. The rocket fires its engines, accelerating at a constant rate, let's say 9.8 meters per second squared, the same as Earth's gravity. From your perspective inside the rocket, you feel pressed down to the floor. If you drop something, it falls to the floor. Everything behaves exactly as if you were standing still on Earth, experiencing gravity. Einstein's equivalence principle says these two situations are not just similar, they're fundamentally the same. There's no local experiment you can do to tell whether you're at rest in a gravitational field or accelerating in empty space. This might seem like just a curious coincidence, but Einstein realized it was the key to understanding gravity. If acceleration and gravity are equivalent, then gravity must have something to do with the geometry of spacetime. Here's why. In special relativity, Einstein had shown that acceleration affects how you experience space and time. An accelerating observer experiences time dilation and length contraction in a direction-dependent way. If gravity is equivalent to acceleration, then gravity must also affect space and time. Being in a gravitational field must change how time flows and how space is structured. This led Einstein to a stunning conclusion. Gravity isn't a force at all. Gravity is the curvature of spacetime. Let me explain this with an analogy. Imagine a flat rubber sheet stretched out tight. If you place a heavy bowling ball in the middle of the sheet, it creates a dip of curvature in the sheet. The rubber around the ball bends downward. Now, if you roll a marble on the sheet near the bowling ball, the marble doesn't travel in a straight line. It curves toward the bowling ball, following the contour of the curved sheet. It might even spiral around the bowling ball before falling into the dip. Einstein's insight was that something similar happens in spacetime. Massive objects like stars and planets create curves in spacetime. Other objects moving through this curved spacetime follow curved paths. We interpret these curved paths as the effect of gravity, but really, the objects are just following the geometry of spacetime. The bowling ball isn't pulling the marble toward it with a mysterious force. The bowling ball curves the sheet, and the marble follows that curve. Similarly, the sun doesn't pull Earth toward it with a gravitational force. The sun curves space-time around it, and Earth follows that curvature. Earth is in orbit because it's following a curved path through curved space-time. From Earth's perspective, it's trying to move in a straight line, but space-time itself is curved by the sun's mass. So that straight line in curved space-time looks like a circle, or really an ellipse, to an outside observer. This is Einstein's general theory of relativity. General because it applies generally to all types of motion, including accelerated motion. And it's all based on the idea that mass and energy curve spacetime. The curvature of spacetime tells matter how to move, and matter tells spacetime how to curve. It's a beautiful feedback loop captured in Einstein's field equations. But wait, how can you curve time? We understand curving space, like the rubber sheet. But time is just time, right? Actually, time curves too. And the curvature of time creates what we experience as gravitational attraction. Imagine two people standing near a massive planet. One person is on the surface. Another is in orbit far above. Both have identical clocks that tick at a steady rate. Because space-time is curved by the planet's mass, time flows at different rates at different heights. Time runs slower closer to the massive object and faster farther away. This is called gravitational time dilation. The person on the surface experiences time passing more slowly than the person in orbit. If they each count 1 million ticks of their clock, more actual time has passed for the orbiting person than for the surface person, even though each experienced 1 million ticks. This time curvature is what creates gravitational attraction. Objects naturally try to move toward regions where time is passing more slowly. This is why things fall down. They're not being pulled, they're moving along the path through space-time where time is most dilated. Think about Earth orbiting the Sun. The Sun's mass curves time around it. Time passes slightly slower closer to the Sun than farther away. Earth's orbit is the path through space-time that balances this spatial motion around the Sun with the temporal curvature created by the Sun's mass. This is hard to visualize because we're used to thinking of 3 dimensions of space and 1 dimension of time as completely separate. But in space-time, they're unified. Curvature affects both space and time together. The mathematics of general relativity describes all of this precisely. Einstein's field equations tell you exactly how much a given amount of mass and energy curves space-time. And they tell you how objects move through that curved space-time. These equations are complex, much harder than special relativity. Einstein spent 8 years, from 1907 to 1915, struggling to develop them. He made mistakes, went down wrong paths, and sometimes felt overwhelmed by the mathematical complexity. He got crucial help from his old friend Marcel Grossmann, who is now a mathematician. Grossmann taught Einstein about non-Euclidean geometry, the mathematics of curved surfaces. This mathematical framework, developed by mathematicians like Bernhard Riemann decades earlier, was exactly what Einstein needed. In November 1915, Einstein finally completed the field equations of general relativity. He presented them to the Prussian Academy of Sciences in Berlin in a series of lectures. The theory was beautiful, elegant, and made clear predictions that could be tested. One prediction involved the planet Mercury. Remember that puzzle about Mercury's orbit precessing slightly more than Newton's laws predicted? Einstein's general relativity explained it perfectly. The curvature of space-time near the Sun affects Mercury's orbit. The effect is tiny because the Sun's gravitational field is relatively weak. But Mercury is close enough to the Sun that the effect is measurable. When Einstein calculated Mercury's orbit using his new field equations, he got exactly the observed precession, 43 arcseconds per century, matching the observations perfectly. Einstein later said that when he saw this calculation work out, his heart trembled with joy. It was the first evidence that general relativity was correct. But the real test came 4 years later, in 1919, with an experiment involving the sun, the stars, and a total solar eclipse. An experiment that would make Einstein world famous and confirm that spacetime really does curve. General relativity made a bold prediction. Massive objects curve spacetime, and this curvature affects not just matter, but also light. Light traveling near a massive object should follow a curved path. This was testable. If you could observe starlight passing close to the sun's gravity should bend the light's path, making the star appear slightly shifted from its true position. There was one problem. You can't see stars near the sun during the day. The sun's brightness overwhelms starlight. But during a total solar eclipse, when the moon blocks the sun's disk, you can see stars that appear close to the sun in the sky. Einstein calculated how much the sun should bend starlight passing near its edge. His general relativity predicted a deflection of 1.75 arcseconds. Newton's theory also predicted bending, but only half as much, 0.87 arcseconds. So an eclipse observation could test whether Einstein's general relativity was correct, whether Newton's simpler gravitational bending was correct, or whether neither theory worked. The opportunity came in 1919. A total solar eclipse would occur on May 29th, visible from a path across the Atlantic Ocean. Totality, the period when the moon completely covers the sun, would last long enough for astronomers to photograph the stars near the sun and measure their positions. Arthur Eddington, a British astronomer, and one of the few people who fully understood Einstein's theory, organized 2 expeditions to observe the eclipse. One team went to the island of Principe, off the west coast of Africa. The other went to Sobral in Brazil. This was remarkable timing. World War I had just ended in late 1918. Einstein was German. Britain and Germany had been enemies. Yet British scientists were organizing an expedition to test a German scientist's theory. It was a beautiful example of how science transcends politics and conflict. The eclipse occurred as predicted. Both teams photographed the stars near the sun during totality. But photographing stars during an eclipse is challenging. The equipment is sensitive. Weather can interfere. Clouds or heat distortions can ruin images. At Principe, clouds were a problem. Only a few usable photographs were obtained. At Sobral, conditions were better, and they got clearer images. After the eclipse, the teams had to carefully analyze the photographs. They compared the positions of stars in the eclipse photos to the positions of the same stars photographed at night months earlier, when the sun was in a different part of the sky. The analysis took months. The measurements were at the very edge of what was possible with their technology. Tiny measurement errors could throw off the results. Eddington and his colleagues worked carefully, checking and rechecking their data. Finally, in November 1919, they announced the results. The starlight was indeed bent by the sun's gravity, and the amount of bending matched Einstein's prediction, not Newton's. The average measured deflection was about 1.61 arcseconds, with an uncertainty of about 0.3 arcseconds. This was consistent with Einstein's predicted 1.75 arcseconds and clearly ruled out Newton's 0.87 arcseconds. General relativity passed the test. Space-time really does curve around massive objects. The announcement made headlines around the world. "Lights all askew in the heavens," declared the New York Times. Einstein theory triumphs. Overnight, Einstein became a celebrity, perhaps the most famous scientist in the world. The public was fascinated by the idea that space itself could bend, that light could be deflected by gravity, that Newton's laws, which had seemed like eternal truths, were actually just approximations. Einstein himself was confident but modest. He had believed his theory was correct, even before Eddington's confirmation. When asked what he would have done if the eclipse observations had contradicted his theory, Einstein reportedly replied, "Then I would feel sorry for the dear Lord. The theory is correct." This wasn't arrogance. Einstein had such faith in the logical and mathematical beauty of general relativity that he felt it must be correct. The theory explained so much: Mercury's orbit, the equivalence of gravity and acceleration, the unification of space and time. It would have seemed like a cosmic injustice if nature didn't work this way. But science requires evidence, and Eddington's eclipse observations provided it. General relativity wasn't just a beautiful mathematical theory. It accurately described how the real universe works. Over the decades since 1919, general relativity has been tested again and again in increasingly precise ways. Every test has confirmed Einstein's predictions. Modern measurements of light bending by the sun are far more accurate than Eddington's eclipse observations. Radio telescopes can observe distant quasars, extremely bright objects in the distant universe, and measure how their positions shift when the sun passes nearby in the sky. These measurements match Einstein's predictions to a fraction of a percent. We've observed light from distant galaxies being bent by massive clusters of galaxies in between us and those distant galaxies. This creates gravitational lensing. The cluster acts like a lens, bending and magnifying the light from galaxies behind it. Sometimes this creates multiple images of the same distant galaxy, or distorts the galaxy into arcs and rings. Gravitational lensing has become an important tool in astronomy. By studying how light is bent, astronomers can map the distribution of mass in galaxy clusters, including dark matter that doesn't emit light. They can measure distances to very distant objects. They can even detect planets orbiting other stars through a technique called gravitational microlensing. All of this is based on Einstein's insight that mass curves spacetime, and that curved spacetime bends the path of light. But light bending isn't the only prediction of general relativity that's been confirmed. Remember gravitational time dilation? Time runs slower in stronger gravitational fields. This has been tested with incredible precision. In 1976, scientists launched a rocket carrying an atomic clock to an altitude of 10,000 kilometers. They compared this clock to identical clocks on the ground. The rocket clock, being farther from Earth and experiencing weaker gravity, ran slightly faster than the ground clocks. The difference was tiny, only a few parts in 10 billion, but it matched general relativity's predictions perfectly. Even more impressively, in 2010, scientists at NIST, the National Institute of Standards and Technology, measured gravitational time dilation over a height difference of just 33 centimeters, about 1 foot. They used incredibly precise optical atomic clocks and found that the higher clock ran faster than the lower clock by a few parts in 10 to the power of 17. That's like measuring a difference of 1 second in 3 billion years. And again, it matched Einstein's predictions. This is why GPS satellites have to account for general relativity. The satellites are about 20,000 kilometers above Earth's surface, experiencing weaker gravity than we do on the ground. According to general relativity, their clocks run about 45 microseconds per day, faster than clocks on Earth, due to this gravitational time dilation. There's also a special relativity effect. The satellites are moving fast, so their clocks run slow due to time dilation from motion. This effect is about 7 microseconds per day. The net effect is that satellite clocks run about 38 microseconds per day, faster than Earth clocks. If GPS didn't correct for this, errors would accumulate quickly. After just 1 day, GPS would be off by about 10 kilometers. After a week, it would be useless. The fact that your phone's GPS works accurately every day is proof that general relativity is correct. General relativity also explains a phenomenon called the Shapiro time delay. Light traveling near a massive object not only gets bent, it also takes longer to make the journey than you'd expect if you just calculated the geometric distance. This is because space-time is curved. The light is following the shortest path through curved space-time, but that path takes longer than the straight line distance would suggest. It's like how the shortest path between 2 points on a curved surface, like a globe, is longer than the straight line distance would be if you could tunnel through. Scientists have measured the Shapiro delay by bouncing radar signals off planets like Venus and Mercury when they're on the far side of the Sun. The signals take slightly longer to make the round trip when passing near the Sun than when the planets are elsewhere in their orbits. The delay matches Einstein's predictions. Every test, every observation, every experiment confirms that general relativity correctly describes how gravity works. Gravity isn't a force reaching across space. It's the curvature of space-time itself. This understanding leads to predictions that sound like science fiction. If space-time can curve slightly around the Sun and planets, what happens near extremely massive, dense objects? What if you have so much mass concentrated in such a small space that space-time curves back on itself? Einstein's equations predict that such objects can exist. Objects where space-time is curved so extremely that nothing, not even light, can escape. Regions of space cut off from the rest of the universe, hidden behind a boundary called an event horizon. These objects are called black holes, and they're among the strangest, most extreme consequences of general relativity. Places where space-time itself seems to break down, where the rules of physics reach their limits, where reality becomes almost incomprehensibly bizarre. But before we dive into black holes, we need to explore another prediction of general relativity: one that took nearly a century to detect, but which finally revealed itself in 2015 in one of the most spectacular scientific discoveries of all time. I'm talking about gravitational waves ripples in space-time itself, traveling across the universe at the speed of light, carrying information about the most violent cosmic events. Events like colliding black holes, exploding stars, and perhaps even the Big Bang itself. When Einstein developed general relativity, he discovered something surprising in his equations. Space-time isn't just curved by mass, it can also ripple. Like throwing a stone into a pond creates ripples on the water's surface, violent cosmic events can create ripples in the fabric of space-time itself. These ripples are called gravitational waves, and they're one of the most remarkable predictions of general relativity. Imagine you have two black holes orbiting each other. Each black hole curves space-time around it dramatically. As they orbit, they stir up space-time, creating distortions that travel outward at the speed of light. These distortions are gravitational waves. They're literally waves in space-time alternating compressions and stretches of space itself, propagating through the universe. As a gravitational wave passes through you, space itself expands and contracts rhythmically. If you were standing with your arms outstretched, a gravitational wave would make the distance from your left hand to your body increase and decrease slightly, while the distance from your right hand to your body would decrease and increase in the opposite rhythm. The effect is incredibly tiny. Even from violent cosmic events like colliding black holes, the gravitational waves reaching Earth cause space to stretch and shrink by less than 1,000th the width of a proton. That's a ridiculously small amount, much, much smaller than an atom. For decades, this seemed impossible to detect. How could you possibly measure such an incredibly tiny change in distance? Einstein himself thought gravitational waves could never be directly observed, though he believed they existed in principle. But scientists are persistent. If general relativity predicted gravitational waves, they wanted to find them. The first indirect evidence came in the 1970s. Astronomers Russell Hulse and Joseph Taylor were studying a system called the binary pulsar-2 neutron stars orbiting each other, with one star emitting pulses of radio waves like a lighthouse. By carefully timing these pulses over several years, Hulse and Taylor measured the orbit of the neutron stars with extraordinary precision, and they found something remarkable. The orbit was shrinking. The two neutron stars were spiraling closer together, very slowly. General relativity predicts this should happen. As the neutron stars orbit, they generate gravitational waves. These waves carry energy away from the system. As the system loses energy, the orbit shrinks and the stars spiral closer together. Hulse and Taylor calculated how fast the orbit should be shrinking due to gravitational wave emission, according to Einstein's equations. The observed orbital decay matched the prediction almost perfectly. This was strong indirect evidence that gravitational waves exist. Hulse and Taylor won the Nobel Prize in Physics in 1993 for this discovery. But scientists still wanted to detect gravitational waves directly, to actually measure space-time rippling as a wave passes through. In the 1990s, two enormous detectors were built in the United States specifically to detect gravitational waves. They're called LIGO, the Laser Interferometer Gravitational Wave Observatory. There are 2 LIGO detectors, one in Louisiana and one in Washington State. Each LIGO detector consists of 2 4-kilometer-long arms arranged in an L shape. Laser beams travel down each arm, bounce off mirrors at the ends, and return to the corner where the arms meet. The beams are combined, and any difference in the time it takes light to travel down each arm creates an interference pattern. If a gravitational wave passes through the detector, one arm would be stretched while the other is compressed, and vice versa. This would change the travel time of the light beams and create a measurable change in the interference pattern. But remember, the stretching and squeezing from a gravitational wave is incredibly tiny. Even the enormous arms of LIGO only change length by about 1/10,000th the width of a proton when a gravitational wave passes. To detect such a tiny change, LIGO had to be astonishingly sensitive. The mirrors had to be positioned to within a fraction of the width of an atom. Vibrations from earthquakes, passing trucks, ocean waves, even thermal vibrations of the atoms in the equipment had to be filtered out or accounted for. LIGO began operating in 2002, but for years it didn't detect anything. The instruments underwent major upgrades, becoming advanced LIGO, which was much more sensitive. It came back online in September 2015, and then on September 14, 2015, just days after the upgraded detectors turned on, both LIGO detectors recorded a signal, a clear, unmistakable ripple in spacetime. The signal lasted only a fraction of a second. It started at a low frequency, about 35 cycles per second, and quickly increased to 250 cycles per second before fading away. The pattern was exactly what Einstein's equations predict for 2 black holes spiraling together and merging. The scientists analyzed the signal in extraordinary detail. From the pattern of the gravitational wave, they could determine the masses of the black holes, about 29 and 36 times the mass of the Sun. They could tell how fast they were orbiting as they merged. They could calculate how much energy was released. The amount of energy emitted in gravitational waves during this merger was staggering. In the final fraction of a second, the merging black holes emitted more power in gravitational waves than all the stars in the observable universe combined emit in light. Of course, this power was spread over a tiny fraction of a second, but still, it was an almost incomprehensibly violent event. The signal appeared in the Louisiana detector 7 milliseconds before it appeared in the Washington detector. This timing difference told the scientists which direction in the sky the signal came from. The event occurred about 1.3 billion light years away in the southern sky. The discovery was announced in February 2016 to enormous fanfare. It was one of the most important scientific discoveries in decades. Gravitational waves were real. Space-time really does ripple. Black hole mergers really happen. And we now had a completely new way to observe the universe. The scientists who led LIGO Rainer Weiss, Barry Barish, and Kip Thorne were awarded the Nobel Prize in Physics in 2017. Since that first detection, LIGO and other gravitational wave detectors have detected dozens more events. Most are black hole mergers, but some are neutron-star mergers. In August 2017, LIGO detected gravitational waves from two neutron stars colliding. This event was historic because telescopes could also see it. Neutron-star mergers produce enormous amounts of light across the electromagnetic spectrum: gamma rays, X-rays, visible light, infrared, radio waves. For the first time, humanity observed a cosmic event with both gravitational waves and light. It was like suddenly being able to both see and hear something you'd only been able to see before. The combination provided an incredible wealth of information. Scientists learned that neutron-star mergers create heavy elements like gold and platinum. The collision sprays neutron-rich material into space, which undergoes nuclear reactions forming these elements. Much of the gold in the universe, including the gold in any jewelry you might own, was likely created in neutron-star mergers billions of years ago. They also tested whether gravitational waves travel at the speed of light. General relativity predicts they should. The gravitational waves and the light from the neutron-star merger arrived within about 1.7 seconds of each other after traveling 130 million light years. This confirmed that gravitational waves do indeed travel at the speed of light, just as Einstein predicted. Gravitational wave astronomy has opened an entirely new window on the universe. Before, we could only observe the cosmos through electromagnetic radiation light, radio waves, X-rays, and so on. Now we can also observe through spacetime ripples. This is huge because gravitational waves pass through matter almost without interacting. Light can be blocked by dust, absorbed by gas, or scattered by obstacles. But gravitational waves travel through everything almost unimpeded. They carry information from regions of space we could never see with light. For example, when two black holes merge deep inside a galaxy obscured by dust, we'd never see it with traditional telescopes. But gravitational waves emerge from the merger and travel to us across the universe, carrying detailed information about the event. Gravitational wave detectors are like ears, hearing the universe, while telescopes are like eyes, seeing it. Using both together gives us a much richer understanding of cosmic phenomena. Future gravitational wave detectors will be even more sensitive. LISA, the Laser Interferometer Space Antenna, is a planned space-based detector with arms millions of kilometers long. It will detect lower frequency gravitational waves from much more massive black holes, including the supermassive black holes at the centers of galaxies. LISA might even detect gravitational waves from the Big Bang itself. In the first moments after the universe began, quantum fluctuations in spacetime might have generated a background of gravitational waves. Detecting this primordial gravitational wave background would give us information about the universe when it was a tiny fraction of a second old. Gravitational waves validate Einstein's vision in a profound way. Space and time really are unified fabric. This fabric can curve, and it can ripple. Mass and energy shape spacetime, and spacetime tells mass and energy how to move. It's an elegant dance, predicted by mathematics and confirmed by observation. But general relativity also predicts something even more extreme than gravitational waves. objects so dense and so massive that they curve space-time infinitely, creating regions from which nothing can escape. Regions where time itself stops and space becomes infinitely curved. These objects are black holes. And they're where Einstein's beautiful theory seems to break down, revealing limits to our understanding of space-time itself. A black hole is what happens when too much mass is concentrated in too small a space. Space-time curves so extremely that it forms a kind of one-way trap. Anything that crosses a boundary called the event horizon can never come back out. Not even light. The idea of a black hole actually predates Einstein. In 1783, British natural philosopher John Michell proposed that a star could be so massive and compact that light couldn't escape its gravity. He called these dark stars, but Mitchell's reasoning was based on Newtonian gravity. He imagined light as particles being slowed down by gravity, eventually stopping and falling back like a ball thrown upward. This gave the right idea, but for the wrong reasons. Einstein's general relativity provides the correct explanation. A black hole doesn't trap light by slowing it down. It traps light by curving space-time so extremely that all paths, even paths moving at light speed, lead inward. There simply is no outward direction once you're past the event horizon. Let me try to explain this with an analogy. Imagine you're on a gently sloping hill. You can easily walk up the hill or down it. The slope doesn't constrain your motion. Now imagine the hill gets steeper and steeper. Eventually, it's so steep that you can't walk up anymore. You can only go down or stay at the same level. Finally, imagine the hill becomes vertical, then overhanging. Now you can only go down. Even jumping or climbing, you cannot go up. All paths lead downward. A black hole is like that for space-time, but in all directions simultaneously. Past the event horizon, all paths through space-time lead toward the center. It's not that you lack the speed or strength to get out. The geometry of space-time itself makes out impossible. There's no direction that leads away from the center. How does a black hole form? The most common way is when a massive star dies. Stars shine by fusing lighter elements into heavier elements in their cores. This releases energy, creating pressure that holds the star up against its own gravity. But eventually, the fuel runs out. When a star about 20 times more massive than the Sun exhausts its nuclear fuel, it can no longer generate enough pressure to support itself. The core collapses catastrophically in less than a second. The outer layers of the star rebound off the collapsing core and explode outward in a supernova, one of the brightest events in the universe. But the core itself continues collapsing. If the core's mass is more than about 2.5 times the Sun's mass, nothing can stop the collapse. The core compresses smaller and smaller. Atoms are crushed. Electrons and protons are forced together, forming neutrons. For a brief moment, pressure from neutrons might stop the collapse, forming a neutron star, an incredibly dense object where a teaspoon of matter weighs 1 billion tons. But if there's too much mass, even neutron pressure can't stop it. The collapse continues. The core shrinks past the point of no return, creating an event horizon. A black hole is born. The event horizon is not a physical surface. It's a boundary in spacetime. It's the point where spacetime is curved so much that the escape velocity equals the speed of light. Since nothing can travel faster than light, nothing inside the event horizon can escape. The size of the event horizon is called the Schwarzschild radius, named after Karl Schwarzschild, who found the first solution to Einstein's field equations describing a black hole. For a non-rotating black hole, the Schwarzschild radius depends only on the mass. For Earth's mass, the Schwarzschild radius would be about 9 millimeters. If you could compress Earth into a sphere less than 2 centimeters across, it would become a black hole. For the Sun's mass, the Schwarzschild radius is about 3 kilometers. A black hole with 1,000,000 times the Sun's mass would have a Schwarzschild radius of about 3 million kilometers. So more massive black holes have larger event horizons. This sounds wrong at first. Shouldn't a more massive object have stronger gravity and a smaller size? But remember, the event horizon is where the escape velocity equals light speed. For a more massive object, this happens farther from the center. What happens inside a black hole? This is where things get truly strange, and where our understanding starts to break down. According to general relativity, at the very center of the black hole is a singularity, a point where space-time curvature becomes infinite. All the mass of the black hole is compressed into a single point of zero volume and infinite density. This seems physically absurd. Infinity doesn't typically show up in nature. When a theory predicts infinity, it usually means the theory is breaking down, reaching the limits of its applicability. Most physicists believe that general relativity is not the full story inside a black hole. At extremely small scales and high densities, quantum mechanics must become important. We need a theory of quantum gravity to truly understand what happens at the singularity. But we don't have a working theory of quantum gravity yet. This is one of the biggest unsolved problems in physics. So the singularity remains a mystery. Even outside the singularity, inside the event horizon, things are bizarre. Time and space swap roles in a sense. Outside the event horizon, you can move freely in space, but are forced to move forward in time. Inside the event horizon, you're forced to move toward the singularity. In the same inexorable way, you're forced to move toward the future outside. Falling toward the singularity isn't something you can avoid or change direction from, any more than you can avoid moving into the future outside the black hole. It's built into the geometry of spacetime. From the outside, a black hole looks frozen in time. If you watch someone fall toward the event horizon, you see them slow down. As they approach the horizon, they appear to move slower and slower, and their image becomes dimmer and redder. You never actually see them cross the horizon. They seem to freeze just outside it, fading away. This is gravitational time dilation at the extreme. Time is so dilated near the event horizon that from an outside perspective, it takes infinite time to reach it. But from the perspective of the person falling in, nothing special happens at the horizon. They cross it in a finite amount of time. From their point of view, they fall through the horizon and continue toward the singularity. The whole journey from horizon to singularity might take only seconds for a stellar mass black hole. This difference in perspectives is one of the weirdest aspects of black holes. Different observers experience radically different versions of events. There's another strange effect called spaghettification. Near a black hole, tidal forces become extreme. Remember, tidal forces are differences in gravitational pull across an object. If you're falling feet first into a stellar mass black hole, your feet are closer to the black hole than your head. They experience stronger gravitational pull. The difference in pull becomes so extreme that your body would be stretched like spaghetti, torn apart by tidal forces. For a stellar mass black hole, this happens before you reach the event horizon. For a supermassive black hole millions or billions of times, the sun's mass, the tidal forces at the event horizon are actually gentle. You could cross the horizon without being torn apart, but you'd still be doomed, as you'd eventually hit the singularity, where tidal forces become infinite. Black holes also have another weird property. They have no hair. This is a phrase coined by physicist John Wheeler. It means that a black hole is characterized by only three properties: mass, electric charge, and angular momentum, that is spin. Everything else about the matter that formed the black hole, what elements it was made of, how it was arranged, all the complex structure is lost. Once the matter crosses the event horizon, all that information disappears. From the outside, you only see a simple object defined by three numbers. This creates a problem called the black hole information paradox. Quantum mechanics says that information cannot be destroyed, but black holes seem to destroy information. What happens to it? Stephen Hawking made this paradox even worse in 1974 with a discovery that shocked everyone. He showed that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. This is called Hawking radiation. The mechanism is subtle. Near the event horizon, quantum fluctuations create particle-antiparticle pairs that normally would immediately annihilate. But if one particle falls into the black hole while the other escapes, the escaping particle appears as radiation coming from the black hole. This radiation carries energy away from the black hole, causing it to shrink. Over extremely long times, a black hole will evaporate completely, vanishing in a final burst of radiation. For a stellar mass black hole, this process takes far longer than the current age of the universe, 10 to the 67 years or more. But eventually, the black hole disappears. So what happens to the information? If the black hole evaporates completely, and the Hawking radiation is random and carries no information about what fell in, then the information is destroyed. But quantum mechanics says this can't happen. This paradox has haunted physics for decades. Various solutions have been proposed. Maybe information is encoded in the Hawking radiation in subtle ways. Maybe it's stored in remnants left when the black hole evaporates. Maybe the paradox reveals that general relativity and quantum mechanics are incompatible and need to be reconciled. We don't know the answer yet. But the paradox highlights that black holes are places where our two great theories, general relativity and quantum mechanics, clash. They're laboratories for probing the limits of our understanding. Despite these mysteries, we know black holes exist. We've detected them through their gravitational effects on nearby stars. We've seen X-rays from hot gas swirling into black holes. We've detected gravitational waves from black hole mergers. In 2019, scientists even produced the first direct image of a black hole. Using a planet-sized network of radio telescopes called the Event Horizon Telescope, they imaged the supermassive black hole at the center of the galaxy M, 8755 million light-years away. The image shows a dark central region, the shadow of the black hole, and its event horizon surrounded by a glowing ring of hot gas. It's exactly what Einstein's equations predict. It's proof that space-time really does curve to such extremes that not even light can escape. Black holes are perhaps the most dramatic manifestation of space-time curvature. But they're not the only way space-time can surprise us. Einstein's equations also allow for other strange possibilities: tunnels through space-time, closed time loops, regions where time flows backward. These ideas sound like science fiction, but they emerge naturally from the mathematics of general relativity. Whether they actually exist in nature is a different question, but they show just how flexible and strange space-time can be. If space-time can curve, twist, and fold, could it curve so much that two distant points in space are connected by a shortcut? Could there be a tunnel through space-time, a wormhole, connecting places that are otherwise far apart? The answer, according to Einstein's equations, is yes. Such structures are mathematically possible. The first person to discover wormholes in the equations of general relativity was Ludwig Flamm in 1916, just months after Einstein published the theory. Later, Einstein himself worked with physicist Nathan Rosen to study these structures, and for a while they were called Einstein-Rosen bridges. Imagine space as a flat sheet. 2 points on the sheet are separated by a distance. But what if the sheet is folded so the 2 points are close to each other and a tunnel connects them? The distance through the tunnel could be much shorter than the distance along the sheet. This is a wormhole, a shortcut through space-time connecting 2 distant regions. In principle, you could enter one mouth of the wormhole and emerge from the other mouth instantly, even though the mouths might be light years apart. This sounds like a perfect way to travel across the universe. Just find or create a wormhole, and you can reach distant stars in seconds, instead of spending decades or centuries traveling through normal space. But there are enormous problems with this idea. First, natural wormholes, if they exist at all, are probably microscopic and short-lived. Creating or enlarging a wormhole to useful size would require forms of matter and energy we don't have. Second, wormholes are unstable. The mathematics shows that a wormhole would collapse almost instantly unless it's held open by exotic matter with negative energy density. This is allowed by quantum mechanics in principle, but we've never observed such matter in large amounts, and it's not clear if it can exist in the quantities needed. Third, even if you could stabilize a wormhole, traveling through it might not be faster than light in a meaningful sense. The relationship between the time experienced by a traveler and the time that passes in the external universe is complicated. You might not actually be able to use a wormhole to reach distant places before light could get there. But the most serious problem with wormholes is that they could potentially allow time travel. And time travel creates paradoxes that seem to violate the laws of physics. Here's how it could work. Imagine you have a wormhole with two mouths initially closed together. You take one mouth and accelerate it to near light speed, then bring it back. Due to time dilation, less time passes for the moving mouth than for the stationary mouth. Now the two mouths are different ages. If you look through the wormhole, you're looking into the past. If you step through from the younger mouth to the older mouth, you emerge before you left. You've traveled backward in time. This creates the possibility of paradoxes. The most famous is the grandfather paradox. Suppose you travel back in time and prevent your grandfather from meeting your grandmother. Then your parents are never born, so you're never born. But if you're never born, you can't travel back in time to prevent your grandparents from meeting. It's a logical contradiction. Physicists have proposed various resolutions. One idea is the Novikov self-consistency principle, which says that the laws of physics prevent paradoxes. If you try to change the past, something always stops you. You can travel back in time, but you can't change history. Events always happen consistently. Another possibility is the many worlds interpretation. When you travel back and change something, you don't change your past, you create a new timeline, a parallel universe where events unfold differently. Your original timeline still exists, but you're now in a different one. A third possibility is that time travel to the past is simply impossible. Maybe the universe has some built-in mechanism that prevents closed time loops from forming. Stephen Hawking called this the chronology protection conjecture. Nature, he suggested, protects causality. So far, we have no definitive answer. Time travel to the past might be possible, or it might be forbidden by physics. We need a better understanding of quantum gravity to know for sure. Time travel to the future, on the other hand, is definitely possible and has been observed. Time dilation means that if you travel at high speeds or spend time in a strong gravitational field, you age less than people who don't. This is traveling to the future in the sense that you skip over time. If you got on a spaceship and traveled at 99.9% the speed of light for what feels like 10 years, then returned to Earth, you'd find that over 200 years had passed on Earth. You've effectively traveled 200 years into the future, though you only aged 10 years. This is the basis of many science fiction stories. Astronauts traveling to distant stars return to find Earth in the far future. From their perspective, they've time traveled forward, though they simply experienced normal time at high speeds. This form of time travel is real and consistent with physics, but it only works in one direction forward. You can skip to the future, but you can't return to your starting time without backward time travel, which may be impossible. Beyond wormholes and time travel, Einstein's equations allow other exotic solutions. There are rotating black holes, which are different from the simpler non-rotating ones we discussed earlier. Inside a rotating black hole, space-time is dragged around in the direction of rotation. This creates bizarre effects, including regions where you're forced to move in circles, even if you try to go straight. There are also solutions describing the entire universe cosmological solutions. These describe how the universe evolves over time, how space-time expands, and what the large-scale structure of the cosmos is. In fact, general relativity led to one of the most shocking discoveries in astronomy. The universe is expanding. Galaxies are moving apart from each other as space itself stretches. This expansion implies that in the past, the universe was smaller and denser. Going back far enough, you reach a moment when all space and time emerge from an initial singularity, the Big Bang. This is another place where general relativity seems to break down. At the Big Bang, the universe had infinite density and temperature. The equations give nonsensical results. We need quantum gravity to understand what really happened in the first moments. But from a fraction of a second after the Big Bang onward, general relativity describes the evolution of the universe beautifully. It predicts the expansion rate, the formation of structure, even the existence of the cosmic microwave background, the afterglow of the Big Bang that we can still detect today. General relativity has been one of the most successful scientific theories ever created. It explains everything from the orbit of Mercury to gravitational waves, from colliding black holes to the expansion of the entire universe. It's been tested again and again for over a century, and it keeps passing every test. But we know it's not the complete story. General relativity and quantum mechanics, our other great theory describing the universe at the smallest scales, don't fit together. At the extremes, in black hole singularities, and at the Big Bang, the theories clash. Reconciling them is the holy grail of theoretical physics. It would give us a theory of quantum gravity, a complete description of space-time that works at all scales, from the tiniest quantum fluctuations to the vast cosmos. This quest has occupied some of the brightest minds in physics for decades, and the ideas that have emerged are as strange and beautiful as anything Einstein imagined. Ideas that space-time itself might be an illusion, emerging from something deeper. Ideas that there are extra dimensions we can't see. Ideas that the universe is a hologram, a projection from a lower dimensional boundary. These are the frontiers where our understanding of space-time is being pushed to its limits, where we're trying to answer the deepest questions. What is space-time really? How does it emerge? What lies beyond our current theories? We've seen that general relativity describes space-time beautifully at large scales: planets, stars, galaxies, the entire universe. But what happens at the smallest scales? What is space-time like at the tiniest distances? To answer this, we need to bring in quantum mechanics, our other great theory of physics. Quantum mechanics describes the behavior of particles, atoms, and subatomic particles. It tells us that at tiny scales, energy comes in discrete chunks called quanta. Particles can behave like waves. You can't know both the exact position and exact momentum of a particle simultaneously. Quantum mechanics is strange, but it's been tested more thoroughly than perhaps any other scientific theory. It explains chemistry, electronics, lasers, superconductivity, and countless other phenomena. It's the foundation of modern technology. But quantum mechanics and general relativity don't work together. They're based on different principles and use different mathematics. When you try to apply both to the same situation, like the inside of a black hole or the earliest moments of the Big Bang, the equations break down. This incompatibility suggests that both theories are approximations of something deeper. Neither is the complete truth. We need a unified theory that includes both a theory of quantum gravity. One of the biggest questions is whether space-time is smooth and continuous at all scales, or whether it breaks down at small enough distances. In general relativity, space-time is a smooth fabric. You can zoom in to arbitrarily small distances, and space-time is still there, still smooth and continuous. But quantum mechanics suggests this might not be true. There's a fundamental scale in physics called the Planck length. It's incredibly small, about 10 to the minus 35 meters, or a trillion times smaller than a proton. At this scale, quantum fluctuations become so intense that they should affect space-time itself. Physicists believe that below the Planck length, space-time becomes quantum. It might not be smooth anymore. Instead, it might be grainy, foamy, or discontinuous. Space and time might come in discrete chunks, like pixels on a screen, rather than being infinitely divisible. This idea is called quantum foam or space-time foam. At the Planck scale, space-time is constantly fluctuating and churning due to quantum effects. Virtual particles pop into and out of existence. Tiny wormholes might form and collapse. The smooth space-time we perceive is an average over these wild quantum fluctuations. We can't directly observe the Planck scale. It's far too small for any foreseeable technology to probe. The most powerful particle accelerators reach down to scales about 10 to the minus 19 meters, still a million billion times larger than the Planck length. But there are indirect ways to search for quantum gravity effects. Some theories predict that light traveling across the universe might be slightly affected by quantum foam. High-energy photons might travel at slightly different speeds than lower-energy photons if space-time is grainy. Astronomers have looked for this effect by observing gamma-ray bursts, intense flashes of high-energy light from distant cosmic explosions. So far, no deviation from smooth space-time has been found, but the searches continue. Several theories attempt to describe quantum gravity. The most famous is string theory, which proposes that the fundamental building blocks of the universe are not point particles, but tiny vibrating strings. In string theory, different vibration patterns of a string correspond to different particles. An electron is a string vibrating one way, a photon is a string vibrating another way, and so on. Gravity itself is carried by a particular vibration pattern called a graviton. String theory naturally incorporates gravity. In fact, gravity emerges automatically from the mathematics. This was a huge breakthrough when physicists discovered it in the 1970s and 1980s. For the first time, there was a framework that could potentially unify quantum mechanics and general relativity. But string theory comes with surprising requirements. For the mathematics to work, the strings can't vibrate in just our familiar 3 dimensions of space plus 1 of time. They need extra dimensions, typically 6 or 7 additional spatial dimensions beyond the 3 we experience. Where are these extra dimensions? String theory suggests they're curled up incredibly small, at scales close to the Planck length. Imagine a garden hose. From far away, it looks one-dimensional, just a line. But if you zoom in, you see it's actually a two-dimensional surface wrapped into a cylinder. One dimension is large and extended. The other is small and circular. String theory proposes something similar for space. The three dimensions we see are large and extended, but at every point in space, there are additional dimensions curled up so tiny that we can't perceive them. The shape of these extra dimensions determines the properties of particles and forces in our universe. Different shapes give different physics. This is both powerful and problematic. String theory doesn't predict one unique universe. It predicts a vast landscape of possible universes, perhaps 10 to the 500 different possibilities, each with different laws of physics. Another approach to quantum gravity is called loop quantum gravity. Instead of replacing spacetime with strings, loop quantum gravity takes spacetime itself as fundamental, but applies quantum mechanics to it. In loop quantum gravity, space at the smallest scales is made of discrete loops. These loops are woven together into a network called a spin network. Space is not continuous. It's made of quantum building blocks. The area of any surface and the volume of any region can only come in discrete values, multiples of a fundamental quantum of area or volume. Time also becomes discrete in some versions of loop quantum gravity. Instead of flowing smoothly, time would tick forward in tiny jumps, each jump being an incredibly small fraction of a second. Loop quantum gravity has had some success in describing what might happen inside black holes. It suggests that the singularity, the point of infinite density, doesn't actually exist. Instead, quantum effects halt the collapse before it reaches infinite density. The black hole might even bounce, creating a white hole, a region where matter explodes outward rather than collapsing inward. A third approach is called causal dynamical triangulation. This theory models space-time as made of simple geometric building blocks, tiny four-dimensional triangles. By connecting huge numbers of these triangles according to certain rules and simulating their behavior on computers, physicists can study how space-time emerges. Remarkably, when they do these simulations, something like our four-dimensional space-time naturally emerges at large scales. At small scales, space-time behaves differently, suggesting that it has an effective dimension that changes with scale. Yet another radical idea is that space-time isn't fundamental at all. It might be an emergent phenomenon, appearing from something deeper. Think of how temperature emerges from molecular motion. Temperature isn't a fundamental property of individual molecules. It's a statistical property of many molecules moving and colliding. At the microscopic level, there's no such thing as temperature, just particles in motion. But when you have trillions of particles, the collective behavior creates what we experience as temperature. Some physicists think space-time might be similar. At the deepest level, there might be no space and no time. Instead, there might be something more fundamental, perhaps quantum information or quantum entanglement. Space-time would emerge from the interactions of these fundamental entities, like temperature emerges from molecular motion. This idea has gained support from studying something called the holographic principle. This principle suggests that all the information in a three-dimensional region of space can be encoded on the two-dimensional boundary of that region. It's like a hologram. A hologram is a two-dimensional surface, but when you shine light through it, it creates a three-dimensional image. The holographic principle suggests the universe might work similarly. The three-dimensional space we experience might be a projection from information stored on a two-dimensional surface far away. This sounds like science fiction, but it's taken seriously because of discoveries about black holes. Stephen Hawking and Jacob Bekenstein showed that the entropy of a black hole, a measure of how much information it contains, is proportional to the area of its event horizon, not its volume. This is strange. For normal objects, information is stored in the volume, but for black holes, it's stored on the surface. This suggests that in the quantum theory of gravity, information is fundamentally two-dimensional, and the third dimension of space is somehow holographic. Physicists have developed detailed theories called ADS-CFT correspondence that demonstrate this principle mathematically. These theories have been incredibly useful for understanding quantum gravity, even though they apply to spacetimes different from our own. The big question remains, what is spacetime really? Is it made of strings? Is it made of loops? Is it made of triangles? Or does it emerge from quantum entanglement or information? We don't know yet. All these approaches have strengths and weaknesses. None has been conclusively proven or disproven. We're still searching for experimental evidence that could distinguish between them. But the search itself has revealed something profound. Spacetime might not be as fundamental as we thought. The smooth, continuous fabric that Einstein described might be an approximation, a large-scale average of something much stranger and more complex at the smallest scales. This is unsettling, but also exciting. For over a century, we've thought of spacetime as the stage where physics happens. But it might be more like temperature or pressure, a useful concept at human scales that doesn't reflect the deepest reality. If spacetime is emergent, what does that mean for our understanding of the universe? What does it mean for concepts like distance, time, causality? These are open questions, but they show that Einstein's revolution isn't over. We're still discovering new layers to the mystery of spacetime, and each layer reveals that reality is stranger and more wonderful than we imagined. Einstein's general relativity doesn't just describe planets orbiting stars or light bending around massive objects. It describes the universe itself, all of space and time, its origin, evolution, and ultimate fate. When Einstein first applied his equations to the universe as a whole in 1917, he made a discovery that troubled him. The equations predicted that the universe couldn't be static. Space itself must either be expanding or contracting. The universe couldn't just sit still. This contradicted the prevailing belief at the time. Everyone, including Einstein, thought the universe was eternal and unchanging. The stars might move, but space itself was fixed and permanent. To make the universe static, Einstein added a term to his equations called the cosmological constant. This term represented a kind of energy in empty space itself, a repulsive force that could balance gravity and keep the universe from collapsing or expanding. But in 1929, astronomer Edwin Hubble made an observation that changed everything. He measured the distances to distant galaxies and their speeds. He found that distant galaxies are moving away from us. And the farther away a galaxy is, the faster it's moving. This wasn't because galaxies were flying through space. It was because space itself is expanding. The fabric of space-time is stretching, carrying galaxies along with it. Think of it like raisins in a rising loaf of bread. As the dough expands during baking, the raisins move apart from each other. But the raisins aren't moving through the dough. The dough itself is expanding, pushing the raisins apart. Similarly, galaxies aren't moving through space. Space itself is expanding between galaxies, pushing them apart. The farther apart two galaxies are, the more space there is between them, and the faster they move apart. Hubble's discovery meant Einstein's cosmological constant wasn't necessary. The universe wasn't static, it was expanding. Einstein reportedly called the cosmological constant his biggest blunder. But the story of the cosmological constant has a surprising twist we'll come back to later. If the universe is expanding now, that means it was smaller in the past. Wind back the clock far enough, and all the galaxies would be close together. Go back even farther, and the entire universe would be compressed into an incredibly hot, dense state. This led to the Big Bang Theory. About 13.8 billion years ago, the universe began from an extremely hot, dense state and has been expanding and cooling ever since. The Big Bang wasn't an explosion in space. It was an expansion of space itself. There was no center point where it happened. It happened everywhere simultaneously. Every point in space was once incredibly close to every other point. The Big Bang Theory made testable predictions. One was that if the universe started out incredibly hot, there should be leftover heat, a faint glow of radiation filling all of space, cooled by the expansion to just a few degrees above absolute zero. In 1965, Arno Penzias and Robert Wilson accidentally discovered this cosmic microwave background radiation while working with a radio antenna. They detected a faint microwave signal coming from all directions in the sky with a temperature of about 2.7 Kelvin. This was the afterglow of the Big Bang. It's light that has been traveling through space for nearly 14 billion years, stretched by the expansion of space from visible light and ultraviolet to microwaves. It's the oldest light in the universe, released when the universe was only 380,000 years old. The discovery of the cosmic microwave background was one of the greatest confirmations of the Big Bang Theory. It won Penzias and Wilson the Nobel Prize in 1978. Since then, we've studied the cosmic microwave background in exquisite detail using satellites like COBE, WMAP, and Planck. These observations have revealed tiny temperature variations, regions that were slightly hotter or cooler than average when the light was released. These temperature variations are incredibly important. They're the seeds from which all structure in the universe grew. Slightly denser regions had stronger gravity, pulling in more matter. Over billions of years, these small variations grew into galaxies, clusters of galaxies, and the vast cosmic web of structure we see today. The cosmic microwave background has allowed us to measure the age of the universe, its composition, and its geometry with remarkable precision. We know the universe is 13.8 billion years old. Give or take 100 million years. We know space is flat or very close to flat on large scales, not curved like a sphere or saddle. But studying the expansion of the universe led to another shocking discovery. In 1998, two teams of astronomers were measuring distances to very distant exploding stars called Type Ia supernova. These supernovae are so bright they can be seen across billions of light years, and they have a predictable brightness that makes them useful for measuring cosmic distances. The astronomers expected to find that the expansion of the universe was slowing down. After all, gravity should be pulling everything together, decelerating the expansion. Instead, they found the opposite. The expansion is speeding up. Distant galaxies are accelerating away from us. The expansion of space is getting faster over time. This discovery was so unexpected that the teams checked and rechecked their data for over a year before publishing. But the result held up. The universe's expansion is accelerating. What could cause this? Gravity is attractive. It should slow expansion, not speed it up. There must be something else, some form of energy that has repulsive gravitational effects. Physicists call this mysterious energy dark energy, and it makes up about 68% of the total energy content of the universe. That's more than twice as much as all the matter stars, planets, gas, dust, and even dark matter combined. We don't know what dark energy is. The simplest explanation is that it's the cosmological constant that Einstein introduced and then abandoned. Empty space itself might have intrinsic energy, and this energy creates a repulsive gravitational effect that drives the accelerated expansion. But we don't understand why the cosmological constant has the value it does. Theoretical calculations based on quantum mechanics predict it should be enormous, about 10 to the 120 times bigger than what we observe. That's a trillion times larger. This is called the cosmological constant problem, and it's one of the deepest mysteries in physics. Other explanations for dark energy involve new fields or particles we haven't discovered yet, or modifications to general relativity at the largest scales. But so far, all observations are consistent with the simplest explanation, a cosmological constant. The discovery of accelerating expansion won the Nobel Prize in Physics in 2011. And it means that Einstein's biggest blunder might not have been a blunder after all. The cosmological constant appears to be real and plays a crucial role in the universe's evolution. The accelerating expansion has profound implications for the future of the universe. If it continues, and all evidence suggests it will, then the expansion will speed up more and more. Distant galaxies will move away faster and faster until they're receding faster than light. Wait, didn't we say nothing can travel faster than light? That's true for motion through space. But space itself can expand at any rate. Galaxies aren't moving through space faster than light. Space is expanding between us and them faster than light can cross it. Eventually, billions of years from now, all galaxies outside our local group will have been carried so far away by expansion that their light will never reach us. The observable universe will shrink. Future astronomers will see a much emptier cosmos, just our galaxy, a few nearby galaxies, and darkness beyond. The cosmic microwave background will fade away, stretched to such long wavelengths that it becomes undetectable. All evidence of the Big Bang will disappear. Future civilizations will have no way to know the universe began or that it's expanding. This is a sobering thought. We live in a special era when the universe's history is still visible. Billions of years in the future, much of what we know about the cosmos will be impossible to discover. The fate of individual structures depends on dark energy too. If dark energy increases over time, expansion could accelerate so much that eventually it would overcome all forces holding structures together. Galaxies would be ripped apart. Solar systems would be torn apart. Eventually, even atoms would be shredded. This is called the Big Rip, but current evidence suggests dark energy is constant, not increasing. If that's true, the universe faces a different fate, the Big Freeze or heat death. Expansion continues forever, gradually diluting all matter and energy. Stars burn out. Black holes evaporate. Eventually, after 10 to the 100 years or more, the universe becomes cold, dark, and empty. These distant futures are speculative, but they're based on the best understanding we have from general relativity and observations of the universe. General relativity has taken us from understanding falling apples to understanding the origin, evolution, and ultimate fate of the entire cosmos. It's been one of the most successful scientific theories ever created. But as successful as it's been, we know it's not complete. The singularity at the Big Bang, the singularities inside black holes, the incompatibility with quantum mechanics, all these point to limits in our understanding. And there are still mysteries about space-time itself, questions we haven't fully answered, puzzles that might require new physics beyond Einstein's theory. We've journeyed through Einstein's revolution. We've seen that space and time aren't separate, absolute things, but are woven together into a dynamic fabric called space-time. We've learned that this fabric can stretch, curve, ripple, and possibly even tear or tunnel through itself. But after all of this, we still face the deepest question of all. What is space-time really? This isn't just an academic question. It's fundamental to understanding reality itself. For most of human history, we thought space was just emptiness, the absence of things, and time was simply the universal clock measuring change. Newton gave space and time more structure. They became the fixed stage where physics happens. Absolute, unchanging, providing the framework within which matter and energy interact. Einstein revolutionized this view. Space and time became space-time, a dynamic entity that participates in physical processes. Mass and energy tell space-time how to curve. Curved space-time tells mass and energy how to move. But what is this space-time that bends and ripples? What is it made of? Here's where our journey leads to something profound and unsettling. The answer might be nothing, or everything, or something we don't yet have words for. Let me explain. In Einstein's general relativity, space-time is fundamental. It's the most basic thing, the fabric from which reality is woven. you can't go deeper. You can't ask what space-time is made of any more than you can ask what numbers are made of. Space-time just is. But quantum mechanics hints at something different. At the smallest scales, the Planck scale, space-time might not be smooth and fundamental. It might be built from something more basic: quantum loops, strings, information, or something else entirely. If space-time is emergent, if it arises from something deeper, then the smooth, continuous space-time we experience is like the surface of water. From a distance, water looks smooth, but zoom in and you see it's made of individual molecules. The smoothness is an average, an approximation that breaks down at small scales. Similarly, space-time might look smooth at human scales, but become something completely different at the Planck scale. The very concepts of distance and time might lose meaning. The notion of here and there, now and then, might be approximations that don't apply to the fundamental reality. This is deeply strange. It means the stage where we thought physics happens, space-time might itself be an illusion, emerging from processes we don't yet understand. Some physicists take this even further. They suggest space-time emerges from quantum entanglement, a mysterious connection between particles that Einstein called spooky action at a distance. In quantum mechanics, particles can be entangled. Measuring one particle instantly affects the other, no matter how far apart they are. This seems to violate relativity, but it doesn't allow faster-than-light communication, so it's consistent with Einstein's speed limit. But what if entanglement is more fundamental than space-time? What if the connections between entangled particles create the structure we call space? Distance between points might be related to how much entanglement exists between the quantum states at those points. This idea is supported by theoretical work in string theory and quantum gravity. Researchers have shown that in certain toy models, space-time can be constructed from entanglement. Pull apart the entanglement, and space disconnects. Strengthen the entanglement, and space becomes more connected. If this is true, then space is not fundamental. Connection quantum entanglement is fundamental. Space emerges from the pattern of quantum connections between fundamental entities. And time? Time might also be emergent. The flow of time, the distinction between past and future, might arise from the way quantum information evolves and entanglement spreads. At the deepest level, there might be no time, just a timeless quantum state from which the illusion of time emerges. This sounds like philosophy, not physics, but it's grounded in mathematical research and physical theory. Physicists are seriously investigating whether space-time is real or emergent. Here's why this matters. If space-time is emergent, it means our understanding of reality is incomplete in a fundamental way. We've been studying the emergent phenomena curved space-time, gravitational waves, black holes, without understanding the underlying reality. It's like studying thermodynamics, temperature, pressure, heat flow, without knowing about atoms. You can develop accurate laws and make correct predictions, but you're missing the deeper story. Discovering that space-time is emergent wouldn't make Einstein wrong. General relativity would still be correct as an effective theory, a description that works at accessible scales. like thermodynamics works for gases, even though it's really describing molecular motion. But it would reveal a deeper layer of reality. And understanding that layer might unlock new physics, new technologies, new ways of thinking about the universe. It might explain quantum gravity. If space-time emerges from quantum entities, then the problem of combining quantum mechanics and general relativity might be solved by recognizing that general relativity describes an emergent phenomenon, while quantum mechanics describes the fundamental layer. It might explain dark energy and the cosmological constant. If space-time emerges from entanglement, the properties of empty space might depend on how quantum information is structured. This could explain why space has energy and why that energy has the precise value we observe. It might even explain the origin of the universe. If space-time is emergent, the Big Bang might not be a true beginning, but a transition phase change where the quantum state organized itself into something we recognize as space and time. Let's step back and appreciate the journey we've taken. We started with Newton's universe space as an absolute grid, time as a universal clock, both fixed and eternal. Einstein showed us that space and time are unified into space-time, that this space-time is flexible and dynamic, that it curves and stretches and participates in physical processes. Now, cutting-edge physics suggests time itself might be emergent, arising from quantum entanglement or information. With the smooth geometry, we experience being an approximation of something far stranger at the deepest level. Each layer of understanding reveals that reality is not what it seems. Each revolution shows that our intuitions, based on everyday experience, are incomplete guides to how the universe truly works. And yet, despite this strangeness, we can understand it. Using mathematics, experiments, and reason, we can probe beyond our direct perceptions and discover the deeper structures of reality. This is the triumph of human intelligence. We're built to survive on the African savanna, to hunt, gather, and avoid predators. Yet we can understand black holes, gravitational waves, quantum entanglement, and the origin of the universe. We can discover that time dilates, that space curves, that the solid ground beneath our feet is mostly empty space between atoms, that atoms themselves are made of particles that don't have definite positions until measured. Reality is strange, but we can comprehend that strangeness. And with each layer we uncover, we find new beauty, new elegance, new questions to pursue. The mystery of space-time isn't solved. We've peeled back layers, but there are likely more layers beneath. The universe keeps its deepest secrets well hidden, but the search itself is worthwhile. Every answer spawns new questions. Every solution reveals new mysteries. And the journey of discovery is what makes us human. Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." We live in a universe that follows mathematical laws, that has consistent rules, that can be understood through careful observation and logical reasoning. That's not something we should take for granted. It's a profound mystery in itself, but it's also a gift. It means the universe is not arbitrary chaos. There's order beneath the complexity, patterns beneath the confusion, beauty beneath the strangeness. and we get to discover it. And so we reach the end of our journey through space-time. 2.5 hours exploring Einstein's revolutionary discovery that space and time are not what they seem, but are instead woven into a dynamic, flexible fabric that shapes everything in the universe. Let's recap the key insights we've uncovered, because this has been a vast exploration through physics, mathematics, philosophy, and the nature of reality itself. We began in the world before Einstein, where space was absolute emptiness and time was a universal clock ticking the same for everyone. We saw how tiny anomalies began to appear strange results from the Michelson-Morley experiment, Mercury's odd orbit, behaviors that didn't quite fit Newton's framework. We met the young Einstein, a patent clerk working in his spare time, who dared to question the foundations of physics. In 1905, he published his special theory of relativity, revealing that time can slow down and space can shrink when you move at high speeds. The speed of light is constant for all observers, and this constancy forces space and time to be flexible. We explored time dilation, how astronauts traveling at near light speed would age slower than people on Earth, how GPS satellites must account for relativistic effects every day, how the twin paradox shows that acceleration breaks the symmetry between reference frames. We discovered length contraction, how objects moving at high speeds appear shorter, how space itself shrinks from the perspective of a moving observer, how the latter paradox reveals that simultaneity is relative. We learned about Einstein's happiest thought, the equivalence principle, that being in free fall is the same as being in zero gravity, that acceleration and gravity are fundamentally equivalent. This insight led Einstein to spend 10 years developing general relativity. We saw how general relativity reveals that gravity isn't a force pulling objects together, but is the curvature of space-time itself. Mass and energy curve space-time, and objects follow the curves. The sun doesn't pull Earth, follows the curved space-time around the sun. We witnessed the proof of Einstein's theory when Eddington observed starlight bending around the sun during the young 1919 solar eclipse, confirming that massive objects curve spacetime, and that curved spacetime bends the path of light. We explored gravitational waves ripples in spacetime created by violent cosmic events like colliding black holes. We celebrated the 2015 detection by LIGO, proving that spacetime truly can ripple and giving us a completely new way to observe the universe. We confronted black holes regions where space-time is curved so extremely that not even light can escape. We learned about event horizons, singularities, Hawking radiation, and the information paradox. Black holes are laboratories where general relativity reaches its limits. We pondered wormholes and time travel exotic solutions to Einstein's equations that might allow shortcuts through space or journeys backward in time. We confronted the paradoxes these possibilities create and the questions they raise about causality and the nature of time. We dove into quantum gravity, the quest to unite general relativity with quantum mechanics. We explored string theory, loop quantum gravity, emergent space-time, and the holographic principle. We discovered that space-time itself might not be fundamental, but might emerge from something deeper. We witness the expanding universe, Hubble's discovery that space itself is stretching, carrying galaxies apart. We learned about the Big Bang, the cosmic microwave background, dark energy, and the accelerating expansion that will shape the universe's ultimate fate. And finally, we confronted the deepest question: what is space-time really? We discovered that the answer might be that space-time is emergent, arising from quantum entanglement or information, with the smooth fabric we experience being an approximation of something fundamentally different. This journey reveals something profound about science and human understanding. We started with common sense: space is empty, time is universal. Einstein showed us common sense was wrong. Space and time are relative, flexible, unified. Now, cutting-edge research suggests even Einstein's spacetime might be an approximation. Reality has layers upon layers, each more subtle and strange than the last. But here's the beautiful part: we can understand these layers. With mathematics, experiments, and careful reasoning, we can probe beyond our everyday experience and discover truths about the universe that our ancestors couldn't have imagined. Now I want to hear from you. What struck you most about Einstein and spacetime? Was it time dilation and the twin paradox? The curvature of spacetime and how gravity works? Black holes and their mysteries? The possibility that space-time is emergent? Do you think wormholes and time travel are possible? Or does nature prevent them? Do you believe space-time is fundamental or emergent? What do you think the next big discovery about space-time will be? I read every comment. Your insights, your questions, your perspectives, they enrich this community and help me understand what resonates most. So please, share your thoughts below. Speculate freely. Ask the questions I didn't address. That's how we all learn together. If you found value in this exploration, I have a few requests that help this content reach others who might experience the same sense of wonder. First, subscribe to the channel if you haven't already, and turn on notifications. There are more deep explorations coming: the mysteries of quantum mechanics, the search for alien life, the nature of consciousness, the ultimate fate of the universe. Each video is crafted with the same depth and care, designed for people who want to truly understand the cosmos. Second, give this video a like. It helps the algorithm show this content to more curious minds seeking understanding. Third, share this video. Send it to a friend who wonders about the nature of reality. Post it in communities of science enthusiasts. Recommend it to someone looking for something profound and thought-provoking. And fourth, explore the other videos on this channel. Every journey is an expedition into wonder, into the strange and beautiful nature of reality. Before we part, I want to leave you with a final thought. Right now, as you sit or lie wherever you are, space-time is all around you. It's not empty nothingness. It's a dynamic fabric, curved slightly by Earth's mass, stretched slightly by the universe's expansion, rippling occasionally as gravitational waves pass through from distant cosmic collisions. You're not stationary in space and time. You're moving through space-time at nearly the speed of light. You're always traveling at light speed through the 4 dimensions of space-time. Most of that motion is through time, but some of it can be redirected into motion through space. When you stand still, you're moving through time at maximum speed. When you move through space, you're redirecting some of that motion, which is why time slows down for you relative to someone who's stationary. You're not separate from space-time. You're part of it. You're a pattern of matter and energy embedded in the fabric, interacting with it, curving it slightly with your mass, feeling its curvature as gravity. The atoms in your body were forged in stars that exploded billions of years ago. The energy powering your thoughts comes from chemical reactions following quantum mechanical rules. The cells in your body operate according to the laws of thermodynamics and biochemistry. You are, quite literally, the universe becoming aware of itself. Your space-time organized in such a complex way that it can contemplate space-time. Einstein discovered that space and time are unified. He revealed that massive objects curve space-time. He predicted gravitational waves, black holes, time dilation, the expanding universe. But he didn't do this by having some mystical insight or supernatural vision. He did it by thinking carefully, questioning assumptions, using mathematics, and following the logic wherever it led. You have the same capacity. Maybe you won't revolutionize physics. Einstein's achievements were extraordinary, but you can understand what he discovered. You can grasp the strange reality of space-time. You can appreciate the beauty of the mathematics and the elegance of the universe's structure. That understanding is a precious thing. It changes how you see reality. It deepens your appreciation for existence. It connects you to the billions of years of cosmic history that led to this moment. Space-time is curved around you right now. Time is passing slower for you and for someone in orbit above Earth. Gravitational waves are constantly rippling through you from distant black holes. You're participating in the universe's expansion, carried along by the stretching of space itself. You're not separate from any of this. You're immersed in it. You're made of it. And now you understand it at least a little better than before. Einstein once said, "The important thing is not to stop questioning. Curiosity has its own reason for existing. Keep questioning, keep wondering, keep seeking to understand, because the universe is vast, strange, and beautiful, and we've only just begun to explore it." Thank you for joining me on this journey through space-time. Your curiosity, your attention, your engagement, these are what make this channel meaningful. Keep looking deeper. Keep thinking bigger. Keep reaching for understanding, because reality is waiting to reveal its secrets. And the next great discovery about space-time might be closer than we think. Until next time, stay curious.